As wireless standards continue to evolve, many service providers are implementing more multi-antenna techniques like spatial multiplexing MIMO, beamforming, and carrier aggregation. Multi-antenna techniques like beamforming present a unique test challenge, and a common problem we hear from customers is the inability to verify, validate, and visualize the signal at the RF antenna. Hello, my name is Sherry D. Tomasi with Keysight Technologies. This is part 1 of a 3-part video series on addressing beamforming test challenges. This video describes the application and measurement challenges. Part 2 describes key measurements, and Part 3 demonstrates the Keysight multi-channel Lte-A Lte Advanced reference solution that combines multiple phase-coherent PXI vector signal generators and PXI vector signal analyzers with the Keysight industry-leading application software and multi-channel configuration and correction tools to accelerate your test setup so you can gain deeper insight faster. So let's get started with our application expert, Craig Grimley.
Let's focus on how beamforming and spatial multiplexing are used within 3GPP Lte-A. Lte-A defines many downlink transmission modes, which we will only briefly summarize here. Release 8 defines transmission modes 1 through 7, covering SISO, transmit diversity, open-loop single-user MIMO, closed-loop single-user MIMO, closed-loop multi-user MIMO, rank 1 spatial multiplexing, and single-layer beamforming on port 5. Release 9 introduced transmission mode 8, supporting dual-layer beamforming on port 7 and 8. And finally, Release 10 introduced transmission mode 9, supporting up to 8-layer transmissions. For today's discussion, we will focus on transmission modes 7 and 8. Now let's summarize the Lte-A-defined downlink signal processing flow, specifically from a transmission mode 7 and 8 perspective. As with other transmission modes, the PDSEH data transport block information is channel encoded and rate matching applied, producing either 1 or 2 code words which are then mapped onto layers. But note that for transmission modes 7 and 8, the pre-coding block is non-codebook based, and so it is left up to the base station to determine the optimum beamforming precoding to apply. This is based on UE feedback and can also be derived from direct measurement of the uplink sounding reference signal. Also note that beamforming precoding can be dynamic and vary on a per subframe and resource block basis to adapt to changing channel conditions. For demodulation purposes, transmission modes 7 and 8 include the mapping of UE-specific reference signal within each PDSEH resource block. It is important to note that the UE reference signals undergo the same beamforming precoding as per the associated PDSEH data. This concept is illustrated on the processing diagram. The beamforming precoding is calculated by the base station to ideally maximize the signal-to-noise ratio observed by the target UE device. But equally, the chosen precoding will attempt to minimize transmission interference to other UE devices within the same or adjacent cells. As well as producing user-specific beam patterns, the base station also has the capability of shaping a desired sector-wide broadcast beam pattern for common control channel content, which is received by all user devices within the cell. This is possible when the number of beamforming antenna elements is greater than the number of configured cell RS ports. Lte-A defines resource element mappings for each of the following reference signal types: transmission mode 7 single-layer UE-specific reference signals for port 5, transmission mode 8 dual-layer UE-specific reference signals for port 7 and 8, as well as common cell-specific reference signals for port 0 through 3. All these reference signals need to be verified both in terms of baseband correctness and relative magnitude and phase observed at the RF antenna. Let's consider a typical TD-Lte-A MIMO beamforming transmission mode 7 and 8 test configuration. A typical 8-element physical antenna configuration used within TD-Lte-A today is shown. It consists of 2 groups of antenna elements. Each group is cross-polarized at 90 degrees to each other. Antenna group 0 consists of antenna elements 1 through 4, polarized at plus 45 degrees. Antenna group 1 consists of antenna elements 5 through 8, polarized at -45 degrees. Each antenna element within a group is spatially separated by approximately half the RF carrier wavelength. This provides a high degree of antenna element correlation within the antenna group, which is good from a beamforming point of view. Since each of the two groups are cross-polarized relative to each other, there is a low correlation between each of the two antenna groups, which is good from a spatial multiplexing point of view. A typical TD-Lte base station is illustrated, comprising of E node B baseband and remote radio head. The remote radio head provides 8 antenna feeds which are connected to an RF antenna calibration coupler unit for test purposes. Note that the base station calibration of the RF antenna is achieved using a dedicated calibration port connection between the remote radio head and the RF antenna calibration coupler. Verification of the base station calibration performance is a very important aspect of beamforming test. The calibration coupler output is typically fed into an RF downlink channel emulator, shown here in an 8x2 configuration to emulate the downlink channel characteristics. The two channel emulator RF outputs are received by the user equipment test device. In our example, the user equipment test device transmits the uplink signal on 2 output ports, which can be connected to an RF uplink channel emulator in a 2x8 configuration to emulate the uplink channel feedback characteristics. Finally, to complete the feedback loop, the 8 RF outputs from the uplink channel emulator are coupled back into the base station's 8 receive antenna ports.
Thanks, Craig, for the detailed explanation on the application. Common problems we hear from customers are the inability to verify and visualize the beamforming signals at the RF antenna. This includes the calibration performance, the baseband encoding beamforming weightings, and the demodulation of single and dual layer EVM at the RF antenna. The complicated test setup for higher order MIMO, like 4x4 or 8x8 configurations that include hardware connections for phase coherent synchronization for beamforming applications, and managing the physical size and cost as the number of antennas continue to grow. These are very daunting challenges. Be sure to watch the next 2 videos in this series to find out how the Keysight Lte-A LT Advanced Multi-Channel Reference Solution provides the essential elements of a solution to enable you to get to results quickly and with more confidence. Thanks for watching. For more information, be sure to visit us on the web.